Hello everyone. So the plan for today was to discuss quantum basis and quantum states and how can you create it in our framework. So Matt's prepared some nice notebook with some homework even at the end of it, but because I know much more about actual internals, I hope to just improvise and show you how it actually works underneath during this discussion, because yeah, why not? So, and without further ado, I guess I just go ahead and see what the hell is the quantum basis and how can you create it and make it work for our states and operators probably in the end. So the idea here is that every quantum object in our framework has a basis. Quantum states has a quantum basis, operators, measurement operators, quantum channels. Underneath there is a quantum basis. Quantum basis is just some numbers assigned to each particular state, because we work in the discrete space. If you have a quantum state, as you usually have, like already seen yesterday, if you have a simple zero, what it actually means that this get vector actually assigned a vector, right? And it's some computational basis, it has a vector. So if you ask for a basis, you return a quantum basis for the state. And we're just gonna look inside of it and see what it actually is. And then we just look ahead and how to create it. So quantum basis, and if it just contains, first of all, it has some names, as you will probably noticed. If it's a two-dimensional computational basis, it has a 0 ket and then 1 ket. It's a two-dimensional computational basis, right? And each of those is assigned a vector. You can element. If you ask for elements, you actually get each vector, a vector for each of those names, right? Maybe a more convenient property would be just to see an association of the ket with its representation, right? So, for example, if you actually had some arbitrary state, if you give it 4 numbers, it's going to be two-dimensional. Now it's going to automatically have a two-dimensional basis underneath. So there's going to be 4 representations for each individual two-dimensional ket, right? Okay. So another point is that quantum basis is actually more general. Like here you can see that it contains some ket vectors, but because in general for operators there's also brass, this means that you also have like rows and columns, so it distinguishes between those. Usually if you have a quantum state like here, your basis only gonna have an output basis. An output basis basically means that it only contains the ket vectors. But just a preview, if you had an operator like a Hadamard, its basis, if you ask exactly the same thing as above, its association gonna contain like this matrix elements, where each element is some kind of also have a similar representation, which is gonna say it's just like a tensor product of 0 and 0 here, or a tensor product of 1 here, but it's like nicely packed in this combined representation. But underneath it, actually, this combined basis is also just a tensor product of an input basis and an output basis. So it means that it has a representation for brass and ket individually, like this. Sometimes it's a sparse array, sometimes it's not. It doesn't matter. In sparse arrays, it just helps you to pack things more tightly if you have a high dimensional basis. So okay, we'll just go ahead and create some other types of bases. For example, if you just provided an integer, that's how you can create bases basically by yourself without underlying states or operators. So it's a three-dimensional basis. It means now it has a 3 associated names with 3 corresponding representations, right? If I have provided 2 numbers, it's gonna, by default, the first one is gonna be treated as a dimension, and a second one as a multiplicity. So now you're saying a quantum framework to create a basis of 3 qubits, or 3 two-dimensional qubits, right? Now it's a free, it's like this notation. It's hidden by default, but you can kind of see and interpret it as that this is the output state. It's a quantum basis with 3 output qubits and 0 input qubits, right? It's kind of a hidden feature, right? So this is a in total it's a dimensional basis, or you can just provide a list of dimensions, and now you can have like 3 output qubits with 3 different dimensions. All right, you can even specify your own names and your own representation by just giving it an association to a quantum basis like that, and now its association going to contain whatever you give it. So if you, and you can use it, oh, I'm going to show it later, and you can use it to create your states with your custom basis like that. Right, and of course there's all many named bases like that. If you like use an autocomplete feature, why is it skipping? Anyway, have like a Pauli basis like X, Y, and Z, which are related to the eigenvectors of a Pauli matrices. Like, right, you can see the actual representation for all those. You can create states and operators in those bases too. All right. I guess I can also say at this point that maybe there's some questions at this point. Is there some questions? Guess not yet. All right. I just wanted to say some additional feature that on top of the quantum basis. Quantum basis is a higher it's a higher object in this framework. There's a lower one because, as I said, it contains both input and output bases. So it's kind of the same thing that works both for states and operators and other stuff. But underneath, there's a lower level thing, which is just works for a single or input and output channel, you can say like that. And it kind of takes the same arguments. You can also create this QuditBasis. QuditBasis is a single thing without any extra stuff like separating inputs and outputs, and also having a labels like computational and pictures. It's kind of, that's why QuantumBasis is a more high level thing with has like pictures, labels, and QuditBasis doesn't have anything like that. It only contains the associations with the corresponding representation. So it's if you can work with QuditBasis directly if you want to create your quantum basis out of it. All right. So now we're gonna go and describe some creation of quantum states with those custom bases. So as you recall, maybe we already told you about it, how to create quantum states. You just provide a list of amplitudes, right? In the traditional form, you already know what it is. If you provide a list of amplitudes, it's the numbers that's kind of displayed near your gets, right? That's by default, it's a computational basis, so you provide amplitudes for your 0 and 1 ket. Okay, in 3-dimensional, it's going to be similar, but now you have an additional number 2, or it's number 3 if you count from 0. Okay, but now, no, okay, yeah, but if you're gonna this comment says that if you provide less amplitudes, then the power of 2 is going to automatically pad it, because it by default it assumes that you only deal with qubits, so it's going to pad that additional 1 ket by 0, so you don't see it in the traditional form, for example, and its amplitude is actually 0, right? So here's some reminder, I guess, of how to create states. Okay, I guess at this point we could just show some of the examples how we would create state on the different bases. So if you, as a buff, if you have an amplitude for qudit, you can just say in what basis you want to do. You can just provide a name, or you can just provide a whole basis if you want. If you construct it customly with some names, associations, or whatever argument that works for quantum basis, should work for the second argument of your quantum state, specifying what basis you want your quantum state to be in. Right. So now in traditional form, it has a new names that correspond to a new basis, which in this case is Pauli X basis. Right. So and this is the same amplitude. I think it's important to know that it's not converting your computational basis with A and B amplitudes into the Pauli X basis, but you provide amplitudes in this basis. So it's important distinction. It's important to distinguish those. If you want to actually kind of change the basis from this one to your X basis, you just make an additional wrapper. Now if you have this computational basis, you want to convert it to an Pauli X basis. This is how the change of basis works, right? Now it has an actual new amplitude, and now because it's a conversion, this kind of equality holds, right? It doesn't matter whether you change your basis or not, or if you solve it. Sometimes it shows you each individual equality or equation for each of the amplitudes, right? If you solve it, you solve the amplitudes are the same. Okay, maybe something more advanced. Maybe we should try some 2-qubit basis or 2-qubit one in some tensor product of X and Y, or maybe Fourier, like that. Right now it's just a 2-qubit basis and a composite basis, 2-qubit state in a composite basis, where the first qubit is an X basis and the second qubit is in the Fourier basis. So you can do things like that. And the similar stuff as above, changing basis works. And you can obviously do it with the matrix. I guess I can also solve the matrix case. If you have a ABCD density matrix in the X, now it's a mixed state, mixed matrix representation state in the new basis, not the computational one. Okay, what else? Okay, any question at this point? List of the built-in basis states. The actual list, oh yeah, if you don't want to use autocomplete, it's not exposed in the global system context, but you can extract it from package scope. There's a bunch of variables that are not exported from the package in the package scope, and all of the names, usually named variables, usually start with a $sign. So if you want QuantumBasis pictures names, maybe it's a QuditBasis names. I guess it's gonna, yeah. That's how you can get the names for that work for your QuditBasis. So if you actually map QuditBasis or QuantumBasis over it, you get if they don't without any arguments. So either QuditBasis or QuantumBasis should work. Just QuantumBasis assumes that by default you're creating an output thing. Okay. So QuditBasis assumes that you're creating a qubit as an output. Okay, what was the other question? Is it possible to see this basis in block sphere representation? Sure, if you have a quantum state, have a property for quantum states. If you have random P01, for example, have a block sphere plot, I think, or just block sphere, I think. Oh, block sphere. That's the graphical representation for the quantum state, right? So you see the usual basis, but there's no way to customize it. But we can create it here. Just it's a nice idea maybe to customize your bases that you decompose into. By default, yeah. So if you, so it's not going to change if you have an X or 0, 1. It points to this one. It doesn't matter which basis you are creating it. It's going to always point. Oh, that's because I'm not converting a basis, but I providing amplitudes in the X basis, right? So you can move arrow like this. I guess if I do it the other way around, it's going to point to plus. If you want to do in Y basis, it's going to point to R, to the right ket, but 0, 1 going to point to the L. That also works for mixed ones. Random mixed. Make a box sphere when your arrow is not necessarily much shorter than the radius, as expected. We're going to just update this notebook because as soon as I finish with this, I'm going to just put this notebook as I type it in the series materials. Of course, I'm not going to just delete this notebook. Sure, I'm going to upload it. All right. Okay, moving on. What namestates? Yeah, because we are discussing states. Yeah, there's the similar to different quantum basis names. Of course, as already seen, we have a bunch of. You can extract it similarly here. Right. Have a QuditBasis name. We also have a QuantumState names. For some reason, package scope close for additional time, and this is the kind of named states that we can create. Okay, what is the most interesting one? Here's a Werner state. You probably know the Bell state, right? The classic one. QG. Graph state, I think, is actually takes a graph. I don't remember how to use it. That create anything? Oh, it's just list. Right, yeah. So this is like going to be create a state with 7 qubits, which equal to the number of vertices in the graph. I think it's similar that we already showed you last time for the quantum circuit. Have a quantum circuit, the same kind of graph, or similar one. Just compile the circuit or apply it to an empty register state. The resulting state is what the same as this one, maybe, but maybe it's something different. It doesn't look the same. Yeah, it's a loop. It's something different. I don't remember what the graph is. I'm gonna leave it. Just curious, for curiosity's sake. Okay, what kind of? Well, uniform superposition is very common state. Basically, what you get after applying Hadamard to your empty register, right? Uniform superposition is just a simple superposition with the same probability, and you can for each of the ket states. So if you give the number of systems, now it's a uniform superposition across 3 qubits, and you get this thing, right? And this should be the same as applying Hadamard on all 3 qubits on an empty quantum state register of 3 systems. All right. All right. So now I guess I'm gonna tell what you can do with the quantum states besides just creating it. Some arithmetic works, so you can multiply quantum states by some coefficient number. So just symbols, because everything is symbolic. You can add them up, and you get like a resulting state, which is what you would expect it to be, right? One of the things that for people who like nice notation, if you like wanna actually show that you create the state as you usually create it in the usual mathematical notation. If you evaluate your things in place, you can evaluate in place every sub-expression, even inside your input cell, right? For example, if you select your quantum state, you evaluate it in place, you get this nice output summary box, which you can again select and convert to the traditional form, as we already taught you how to do, right? So you can do it like this, and you can do it for every state. And now you have a nice notation which also evaluates to a box, but you can still create. So you can still turn it into a nice traditional mathematical notation. That's a nice trick to know about. Okay. Which are the output forms that you can apply to quantum states? Well, only the traditional form. Traditional form is just yeah, by the way, I should say that whenever we press a form, traditional form, because there's only a traditional form and a normal form. Traditional form is just the same as asking for a formula, maybe formatted differently. Traditional form is just basically asks to show you the formula for the underlying state or operator or measurement operator, channel, and so on. Maybe an exception at a quantum circuit. For a quantum circuit, traditional form is just a diagram. Yeah, and there's no other forms. If you have any suggestions, maybe, because usually it's like what kind of formats there. There's no like distinction between in the Wolfram language. There's just a few forms to work with. You either type things in your cells using the input form. Now, the output form you usually see a standard form, and traditional form usually used for mathematical, nicely formatted notation. There's no like other choices to choose from. There's like a formatting style that's a bit different things, right? Okay, it's kind of side. Okay, you're representing all matrices which are two-dimensional. I mean, polymatrices. I want to know, is it possible to represent general? What do you mean by general? I already showed how to make a arbitrary symbolic matrix, not just Pauli one. So I'm not sure what you mean by general 2x2 matrix. For a basis, maybe you mean can I use a representation that is symbolic? I know you have to clarify it. The unitary matrix. But what do you mean? Whether should I use it? If you're using unitary matrix, you usually mean you have a quantum operator that is unitary, and you could use arbitrary matrix for your operator. And it's a quantum operator story basically. We have to have a quantum operator. Okay, it's a preview of quantum operators, right? We also have different named quantum operators. I think you have U here. See, so you can create U operator. I think it takes 3 arguments. I'm going to create a quantum operator like that, which may be the familiar matrix form to you. This is an operator of the unitary thing. It's a usual representation, very common quantum operator, quantum gate, a parametric one. You can construct any single qubit gate you can just construct by using this guy, up to a global phase, I believe. All right. What else? Normal. The question is, normal is a, when I apply normal is not a quantum function. Normal is a general Wolfram language context that converts different stuff to some normal representation. It's like if you have, for example, if you have a sparse array, like every matrix A, B, C, D again, right? If you convert it to a sparse array, it has this special representation. But it has a normal form, it just looks like a nested list. There's a bunch of stuff in the Wolfram language that can be normalized in this way. And we don't have any normal for quantum states or quantum operators. When I probably called normal and quantum state, I actually called it for the sparse arrays in the association or something like that. I don't remember. Normal doesn't do anything for the quantum states at this point, I think. I'm not sure what it should do. All right, I think I've done with the questions. No more new questions that I haven't answered yet. All right, moving on. What else? We were discussing how we can use states to do some arithmetic on those quantum operators. This is some clarification that's already told you how to do, that you can convert states to a different basis. Yeah, this is just a change of basis. Okay, now we should discuss, I guess, the different functions that we have to work with states and the basic quantum framework functions. So the one very useful one is to do partial tracing of your states. Right? If you have a state, like this state, this is just a single qubit. You just create something like arbitrary. Right? This is a symbolic one, a 2-qubit state. But now, how do we discard or trace out, which are kind of two different operations, but what you usually mean by tracing out one of the systems, because this is a system of 2 qubits. If you want to trace out the second one, that's what you usually get, right? Maybe do the complex expand in this case. Yeah, because it looks like it didn't trace it out, but because when you usually trace out one of the systems, you get a mixed state, right? Because now it's a matrix state of 1 qubit, and because it's a matrix state, it contains two row and column indices, so you have to display it as two kind of things. Usually, this is one of the points that we should have done earlier. If you have a quantum state which is a mixed state or a matrix state, right? Usually see in the literature that you have, like, for example, if you have any random mixed thing, it's a raw density matrix, which is usually abbreviated by raw, right? And you usually prefer to see it as this thing, actually. Not in this notation when you have a double ket, but a bracket notation. So you actually prefer to see your density matrix mixed state as an operator. And we kind of distinguish it because it's very ambiguous when you display your state that looks like an operator, right? Because it's not by default, it's not an operator, it's a state. So it only have to have an output. So it only you have to represent it by a cat. So it's important to distinguish when your state, either it's a pure one or a mixed one, it only should contain cat vectors, right? But an operator, it's something that contains both input and output, so it's allowed to have input and brass and cats. So your mixed state is displayed usually like this. And that's why when you trace it out, your pure state, if you trace one of the qubits of your pure state, you get a mixed one, which is a matrix, and that's why it shows up like this. And if you actually show it as an operator form, maybe that's a more, maybe you together, right? To group some of the things, right? Now it's a more familiar form of a matrix state that you get after tracing out one of the qubits. Okay, and the partial trace, yeah, so the notation for partial trace works for not just states, it works for operators, even for, not shown here, but you actually can trace QuantumBasis itself. And what it means if you have a QuantumBasis, two systems and two different ones, for example, X and Y Pauli basis. If you trace one of them, you just get a new basis. So you can just discard it. In this case, you don't have to trace some arbitrary matrix. In this case, it just means discarding one of the systems completely. So you can use this basis for in your newly created states, for example, or just change basis in this new basis and things like that. All right, so this is the quantum partial trace. By the way, if you have a function, you have like a quantum basis functions, quantum state basis, the documentation already should be come pre-installed with your packlet. So the usual way how you search or browse documentation in your session usually should work for the symbols in the packlet. So it's the same as online documentation in this case. So there's more examples. So the quantum basis and the partial tracing. There should be more examples of how to use it. Yeah. So this is an example of tracing out the quantum basis. All right. Oh, I just realized you maybe haven't seen the notebook that they showed. Yeah, because I was sharing. Hold on. I just wanna show it. What I meant the documentation. What I was showing is the documentation. All right. And that it works. Okay. Moving on. Next, we can test for entanglement. So usually when you create a state of more than one system, so more than one qubit or qubit, right? For example, you can create a mixed state for two qubits in whatever way you like. For example, this is a named Werner state, which creates a mixed state of two qubits. You can ask whether it's entangled or not. And for this particular named state, for the Werner state, there's a property that if you have your probability here is more than half, then it's not entangled. But as soon as you lower it below it, now it becomes entangled. And I can explain, I guess, what is this entanglement test actually is doing in more detail. So what is actually happening? There are a bunch of, oh, okay, I'm just gonna explain it a little bit later. So, and you can do it for other different states. And you can ask which particular systems. If there's more than two, you can ask which pair you want to ask whether those systems entangled or not. Okay, and underneath it, what it's doing is computing something called entanglement monotone on your quantum state. It's some numeric property. We have a bunch of those monotones implemented. By default, I think it's a concurrence, right? The concurrence entanglement monotone is just a number. So you give it a state, and it just computes some metric of what basically describes some kind of degree of entanglement of this state or systems in this state. So, and then there's just some equality that's happening. If it's, for example, this thing is entangled, but this thing is not because it's a zero. And I think the condition is when it's not zero or higher than zero, then it's entangled. And I think it works. This kind of condition works for all kind of different monotones here. So, for example, log negativity for this state that we know is not entangled is still zero. And how this, what is entanglement monotone computes in detail, I also can explain a little bit further. Because when you create a state, because you can test quantum states even if they are not directly shown as a two system states. For example, you can create an arbitrary like 4-dimensional state. Right now it's a 1 qubit. I think you still can ask whether it's entangled or not. Oh yeah, you can do it. And what it's doing underneath, it's bipartitioning your state. There's a property for states called bipartition. You see, by default, before bipartitioning, it was a single 4-dimensional qubit, but after bipartitioning, now it's a 2 qubit, 2-dimensional qubits. And now you can ask of this particular state, because it's an equal one, it should be equal to it. Right? You can ask whether those particular systems that it bipartitioned into, whether those entangled between each other or not. And you can do this bipartition for any kind of state. So it just divides your dimension. There's some maybe a more advanced example would be, for example, if you actually have create not a 4-dimensional one, but some 10-dimensional. Now it's a 10-dimensional thing. And now if you bipartition it, by default, it's gonna create 5 by 2, because 10 is divisible by 5 too. Or you can do it the other way around. If I say the first system, make a first system 2-dimensional. Now instead of 5, 2, it's 2, 5. And if it's some kind of other number that divides, for example, 12, right? You can make 2 by 6, you can make 3 by 4, right? 6 by 2, so on. You can even make 12 by 1 if you want. So it kind of looks like it's the same as before, but in principle, we can support 1-dimensional qubits too. They're not useful, but we can kind of work with them too. All right, I think it's time for questions at this point. All right, if you have any random state, how to check whether the state is pure or mixed? Well, it just says there. It's a random one, right? If you actually create it like that, it says right here. But you can also state there's a property pure state, but you can also ask it for a mixed one. So it's over matrix states, right? This is a mixed state, which is contains a density matrix underneath, but you can still ask whether it's pure or not. Right? It's not pure, but there may be a matrix state that is pure. For example, if you actually convert is a way to do it. It's like if you already created a pure one and you just turn it into a matrix state. Right now it's still a pure state, but which is represented by a matrix or by a density matrix, right? But because I've created it from the pure one, and the density matrix can be only have a single eigenvalue, non-zero eigenvalue. It's a pure one. You can say try to just look at this information in the summary box on the pure state Q property will tell you that it's mixed or pure. Yeah. I guess this information here, besides having possibility for states outside of pure, mixed, and it's also possible to have degenerate, I think. Basically a state with those zeros. I think that's only 3 possibilities there. Oh, and yeah, and it's also unknown. When we unknown matrix, if you have a matrix, maybe symbolic one, for which it's impossible to compute eigenvalues or compare them, but it's a zero, no, it's going to be an unknown state of matrix type. So this is the kinds of states that you can create. Okay, I hope it answers the question. Okay. All right, so now we're just gonna explore some more additional properties of states. Okay, we already explored that we have the way of creating mixed ones, pure ones. Here's just a list of all the properties that a state can have. Like it doesn't matter whether it's a mixed or not. The list of properties would be going to be the same. And now here's also some of the some mention of bipartition that I already did. Okay, decomposition. Well, decomposition is an interesting thing. Yeah, so it's a way of decomposing your state into pure or separable components. I would rather say. So if you have some random 2-qubit system, 2-qubit state like this, right? It's usually some kind of, it looks like some inseparable gets inside of it, but you can decompose it into a sum of products. So for example, if one of all of those are, well, they not look very convincing. Let me do like this. Yes. You can decompose it into a sum. So the outer list says that it's sum and the product, and this is only contains a single qubit state. And you can say kind of, I kind of have it the same here, but it's not for the. Is it? Just I wanted to show it in the computational one because this one is some new basis that we converted it into that looks like basically a single ket vector, which is not normalized. And you can recover, the idea is that you can recover your initial state from this decomposition by just doing the quantum tensor producting each individual pair and then summing it up. This resulting state should be equal to the original one. But you can use this decomposition to do some interesting stuff. Maybe. It depends on your application. All right. Disentangling. This is very common to decomposition, but instead of having a pair of the single qubit things, I think it just already pre-tensor producted it. It's a decomposition, but you tensor product it. And I think if you have a disentangled state like that, if you just sum it over, it should again recover the original one. And we have a bunch of stuff like this. We have a purification, which is a more abstract thing. It's like if you're given some mixed state in 3D and you purify it, well, it means that if you trace out one of the systems, you should get the original one. Right? It's like add one additional purification means it's like asking for what would be the additional system that you have to product it with the original one, so that your output one is a pure one. But if you trace it out, that system that you just added, you recover the original state back. This is the idea of the purification. Okay. Okay, this is some bunch of interesting properties, so maybe there's some questions about them. How anaconizing the state description with just a click? You're asking again about this kind of manipulation. I'm just turning it into a traditional form and normal form. I think I answered this question in the community forum post somewhere, because it's a common one. So maybe just there's an actual key bindings how to do it. All right. All right. What else do we have? Some kind of structural manipulations, because we have a bunch of properties of states here. Some of them are making you decomposing your state, or like purifying it. Those are actually manipulating amplitudes, but there's some also structural things, like if you can just swap states around. So this is like a underlying thing without making the permutation operator and acting on it in the circuits, in the circuit environment. You can just manipulate states directly, for like permuting qubits around. For example, if you had this kind of state, amplitudes going like this, if you permute your first and second qubit, swap them around, you should be seeing amplitude change A2 go to A3, because 0, 1 and 1, 0 should swap around, but everything else stay the same. Yes, this is a just swapped around the qubits. So crisscross those amplitudes around. Okay, what else we have? A projector and operator is a kind of very similar thing. It's operator property I already showed you in relation to density matrix, right? If you had a density matrix state, its operator would look more similar to you in terms of a traditional form. But what it actually is, underneath, if you have a pure mixed matrix state, doesn't matter. Projector is just kind of makes it doubles your, first of all, it doubles your number of systems, so number of qubits. It kind of, because you see, it's like before it had I plus this 2 qubit state. Projector doubles the number of qubits, and also doubles it in a way that creates not an input one, but an output one. And this is kind of a hacky way, because now you can ask, does it look like state anymore? And you're right, because it's not a state. It's a little bit of a hack. Because if you ask for a projector, it says pure map, right? So this way we can represent states. That's how we distinguish states from operator. So operators is kind of can act like states, but they have an additional order, because you can think of operators more like a gates, because you know where you apply it in the circuit environment. But you can still forget about circuits completely and work with pure maps. But they're going to be displayed as states. I don't know how to just explain it more clearly. Basically, we're cheating a little bit here. Our states are more general than actually states. I told you about that it can be either pure one, mixed one, degenerate, or unknown state, but it actually can also be a map. And even depending on whether it contains brass or column vectors inside of it, which it can also do. And if you wrap around, well, basically, if you have an actual quantum state with brass in it, which is a pure map, actually, if you just wrap it with quantum operator, it automatically works. Now it's a more usual representation of this object, if you wish. Sometimes it's just very useful to work with quantum states instead of quantum operators that also have this additional order thing in relation to circuits. All right, maybe we will discuss it a little bit more in more detail later. How can I get a list of name states? I already showed you. A list of, you have to dig inside of the quantum framework code. It's inside of package scopes. We have I guess I can say what kind of different named things we have. That's listed here. You have Qudit names, QuditBasis names. You have QuantumState names. You have quantum operator names. You have quantum channel names. I think I have many quantum measurement operator names, but I think I still have them. Just one. We are not going to include it. And we have quantum circuits. And maybe we also have quantum distances, maybe useful one. And it covers the most of the named stuff that you can just use in relation to those objects. Okay, where were we? Oh, diagram. Diagram is very important, useful thing to know. So okay, it kind of explains this relation of projectors, turning states into operators and back. So, for example, if you have just a pure state like this, you can represent it as a simple diagram. It's not a circuit diagram. It's just a simple graphical object that shows you what is this object in relation to string diagrams. If you know what string diagrams mean, that would be the usual kind of notation of it in the string diagram case. And what it means here just shows you the label and how the outputs and inputs are, how many of them and what are they, basically for your state, operator, channel, whatever it is. For example, your states, when they are actually states, when they say that it's a state, it usually means that you only have some output or multiple outputs. Like here it has one output, here it has two outputs, right? You can have three outputs. But that's what I usually mean by a state. Also, if you take a dagger of your state like this, like now you can turn your state into a bra, or gets into a bra, and your state is technically is called effect. It's another thing, right? And its diagram, It means you turn your diagram around. Now your outputs become inputs. So if you have a diagram that only contains inputs, you technically call it an effect like this, and your diagram, underlying diagram looks like this. And for quantum operators, when you have both of those, you also have a diagram, but now they're gonna be displayed as a box with both inputs and outputs. And usual gates in the quantum circuits, let's take a Fourier one. It can, if you have more, if you operate acts on more than one qubit, it's just gonna have more outputs and inputs, but it's the number of those gonna be the same. That's usually that's what the gates are. They have the same amount of inputs as the outputs, and that's what distinguishes. It's a more advanced thing. What distinguishes usual operators in this framework from the measurement operators? Quantum measurement and channels, and also channels. Quantum measurement operator diagram would actually contain. By default, it's gonna look like it's gonna be some. We'll just change the basis. It's gonna show the basis label, but if it's a projective measurement, it's gonna show up as an operator diagram. But if it's a POVM, or because we turn everything projection, even projective measurement into POVM, in the end, they actually have more additional output. That's what you see in quantum circuits with measurements. For example, if you have diagram for the quantum circuits, you have this additional arrow, right? You have usual operators like this, just have the same number of inputs as outputs. But quantum measurement, you can't squint and pretend that it actually has one more additional output. That output stuff to a classical channel, and that's why this kind of diagram for that only displays its outputs kind of shows it. And you also have the similar one additional output diagram for quantum channels. Create some random channel like bit flip. And this diagram is going to also contain one additional output. It's not shown in the circuit diagram, unfortunately. That's what we are thinking about, how to actually show it, because it's not storing that additional output anywhere. It contracts it immediately. That's the property of quantum channel. So when you measure stuff, you kind of outputting your additional outputs into some classical channel, but how quantum channels act, they also produce this additional output underneath, but you immediately contract it. So that's why you're not displaying it, but it actually underneath it contains this additional thing. So in this sense, quantum measurement and quantum channel are the same thing. All right. What's the shortcut of, okay, how I did the dagger here? Well, the usual do is there's a dagger thing. It's escape DG. That's how you create a dagger symbol, right? But it's a property of the Wolfram language. If you have this dagger symbol in your superscript or power, right, and underneath it interprets it as the super dagger thing. It's a special symbol, and that's when you have this special symbol acting on a state. It knows that you are daggering it, taking it conjugate. We can just, instead of doing this fancy notation, you can just use a property called dagger, which is the same as this. Right. Well, about big picture and books. Well, I don't know. Well, actually, I can advise one more. I have one favorite picture when I learned all this diagrammatic approach to quantum computation and quantum theory in general. It's called Picturing Quantum. So like it's a book recommendation. Picturing quantum diagrams or something. Picturing quantum diagrams. I don't remember. Oh, not the diagrams, processes. Processes. I think it's called something like it's by okay. That's when you can learn all about diagrammatic approach to all about this kind of boxes and how they compose and all other stuffs, all other related stuff. I don't think I have another recommendation, but that's a good one. All right. Okay. Other questions? If you do a circuit diagram, Qiskit, is it pure Qiskit or inverted? Oh yeah, it's kind of we're using an opposite convention to Qiskit one. So as I know, Qiskit numerates it qudits from bottom to up, right? It also it's like if you have a quantum circuit. We just enumerate our qudits in a normal sense. This is like a first one, second, third one from left to right. Right? I think Qiskit does it in a different direction from bottom to up. It also has a measurement line. If you have an actual measurement operator applied to it. Also, Qiskit likes to show the measurement line on the bottom. There's a reason that we, by default, showing it on top. We actually can change it. Measurement wire position, I think. Qiskit likes to show it this way, but there's a reason why we show it by default on the top, and maybe I'm gonna explain next time why. It's related to how do you treat these outputs, because this additional one is on the left, right? For the measurement thing, the classical one is the left one. It makes sense to put it on the left. So if you treat your circuit from left to right, it's on the left to the output. So it kind of makes more sense to put it on the top. So that's my interpretation of it. Parallel computation. So does the framework allow parallel computation? Well, it kind of depends what you mean by that. We have parallel functions, some parallel support in the Wolfram language itself. But if you mean whether we use it anywhere inside of the framework, no, we don't use it anywhere. And there's no there's no many places you can use it, because in what setting you want to use a parallel computation? If you want to compile your circuits parallelly, it's a hard problem already because all the compilation production grade compilation of circuits we can't do anyway. We like rely on something like Qiskit or other frameworks. We have two separate backends into additional to a pure Wolfram language that just constructs tensors in the tensor network. We have some Qiskit translation compiling there, which may be using parallel code in order to do that. But we're not doing parallel directly, unless the construction of tensors doing some parallel computation underneath, which I don't know. Maybe it's doing something parallel, but at least it's a vectorized, nicely vectorized procedures, so they can should work relatively fast if you're just dealing with numeric values, not symbolically. But if your circuits and operators have symbolic values in them, so it's kind of harder. So I doubt it's gonna be some parallelism there. And so I don't know. Not sure how to answer. Okay, how much time do we have left?
We're already 7 minutes over.
Oh yeah, really? So
Yeah.
well, time flies. I just don't remember when it's supposed to end. Okay, but then we should. There's some kind of. Well, I just mentioned that Matt's created some homework for you to do here. I haven't seen what it is all about myself much, but you can save this notebook with the stuff I wrote in it in the materials folder, and you can go ahead and solve some problems that in the end of it, and that should wrap it up.